Hi everyone. So this little mini lecture is going to be a little bit different. Instead of using the textbook, I'm using the PowerPoint slides. Main reason the textbook doesn't actually cover this material. And so I have you look at it for Lab 10 as far as ceiling versus floor effects, as well as regression to the mean, because they're pretty important concepts when we talk about how do you actually interpret data and critically think about it. Obviously on your output, it's going to tell you if something is significant or not, but there's more to interpreting than just looking at the output. There is a major critical thinking component to understand what do the results mean. Are they probably flawed in some sort of way? Can we actually state what we're trying to state? Things like that you need to kind of consider. So here, we're just going to go through two different PowerPoints pretty quickly that kind of covers some of these things to consider when you're interpreting results. So first and foremost, after collecting and analyzing data, next step is to interpret. Again, interpreting is going to be your output, seeing what's significant and what is not, but it's also then going to be why is that significant? Is it truly significant, or did you run into other things? Do you have so many variables that you're collecting that it's just inevitable that you're going to find significance? Those type of things all should be considered at this phase. So various pitfalls may impede correct interpretation, scale attenuation, and regression artifact. So scale attenuation, here we have the ceiling and floor effects. So ceiling effect, performance at upper limit of scale. Example could be a math test so easy that everyone in class gets all the problems correct. Floor effect, performance at the bottom of the scale. Math test so hard that no one in the class can get any problems correct. So to figure out if you have a ceiling or a floor, you need to look at what are your participants actually doing. If they are doing it incredibly well, we call that a ceiling. If they are doing incredibly poor, then we call that a floor. So another example of ceiling effects here, two obese men bet who can lose who can lose the most weight in a set amount of time. Man A actually weighs 300, man B weighs 350. Both weigh in at 300 pounds, maximum possible on a scale. Both lose 100 pounds, but when they reweigh themselves, man A weighs 200, man B weighs 250. Looks like man A lost more weight, but this is inaccurate due to the ceiling effect. Right, so here the ceiling effect is not so much in what your participants were doing, but in the tools that you used. That if you are using some type of measurement tool, you need to make sure what is the range and is there a potential flaw with that range. Here having a scale that goes up to only 300 pounds and then stops can become a potential issue. So you need to kind of recheck all of your tools and equipments. Most of the time we're going to be using things like computer software. Is there floor or ceiling effects that can be present in that software that maybe it taps out after so many minutes spent on a task and it just says, all right, it was 10 minutes, but the person actually spent 15 on it. Things like that become problematic. And it has nothing to do with your participants. You might not even be fully aware that the program does that, but just something to check if you're seeing a lot of people scoring the same thing. Well, is it because that is the maximum or the minimum a lot? So here are just some graphs show you that. Another example, having participants memorize 7-digit phone number, then dial it after 1 minute. Right, most people have no problem holding 7 digits in their working memory, especially if they know that they're going to have to do something with it. So I asked you to memorize these 7, you'd be able to do it, and most people would be very successful on this task. Probably not a good measurement of memory, right? It's too simplistic. You're not really pushing anybody's limits when it comes to memory, so everybody's going to do very well. Now, if you have them try to remember a 30-digit number and you give them 10 seconds to memorize this, odds are nobody is going to be able to do this. So you're going to end up with a floor effect that everybody's going to be failing this task, and you're going to conclude, well, all my participants' memory was flawed or insufficient. And again, it's not the case. It's that the way you design the study is flawed because it's running into these floor and ceiling effects. A hint, if you find a large number of participants are scoring 100% or 0% on your dependent variable, you probably have a floor or ceiling effect. So this is where you would go and check your data. It is always important to check your data as the study is going. So that way you can hopefully catch it and adjust before you have all your data collected. And then you just have to throw all that data away and then restart because you ran into a floor or ceiling effect. So some solutions to this, doing some pilot work. So again, pilot studies, these are just studies that you do before you do the actual study. And you just have a small number of participants and you test how well things are going. Um, I know a lot of times I will run pilot studies just to make sure that the software that I'm using is doing things correctly. So I will use like SurveyMonkey or Qualtrics or some type of survey tool, and I'll have skip logic in there that if you answer a question a certain way, it's going to skip the next step because it doesn't apply to you, and just making sure that that is actually working correctly is one of the reasons I use pilot studies. But kind of byproduct of it is certainly to make sure that the tasks that I'm asking for are actually feasible, reading levels appropriate, all that type of stuff. Let's see, if participants score too low, tasks may be too hard, make it a little bit easier, so on and so forth. All right, so then regression to the mean. So extremely high scores tend to decrease and extremely low scores tend to increase. What this essentially means is that if you give some type of task or exam and you know that the average on that test is 75, if somebody is scoring 100 each time, it's unlikely that they are going to stay that high. They're probably going to drop down somewhat and get closer to the mean of 75. Same thing if somebody scores very low on exam, they're probably not going to stay that low. They're probably going to raise up a little bit as well and get closer to the mean. So here, just kind of reiterating that, student gets 99% on a test, more likely to get a lower score on the next test. Student that gets 10%, more likely to get a higher score on the next test. And again, this is just because if you are scoring perfect on everything, it's very hard to maintain that. So you're likely to mess up and drop down a little bit. And if you are doing incredibly poor on everything, odds are something's going to shift in your environment and you're going to do a little bit better the next time around. Quasi-experimental design susceptible to regression due to lack of random assignment. So again, quasi-experiment means that you can't actually do full-on random assignment. Quasi-experiment might be looking at gender differences. So you compare men versus women. Obviously, you can't do random assignment in that type of study. Example could be participants may be assigned to group A because of a really high score on a task. Group A will probably score less, or at least we'll see the scores decrease next time that they're tested. And so the treatment effects are masked. Performance doesn't get better because regression are in fact tendency to regress toward the mean. So this would be something like if you take all the students who are performing very well in a math class and you say, okay, we're going to move them up to an advanced placement math class, you're probably going to start to see some of their scores drop because you selected them due to their high scores. And again, it's just unlikely that they're going to maintain that level. Other example, participants may be assigned to group B because of really low scores on a task. Odds are those scores are likely to increase again because of regression to the mean. So the treatment effects may be inflated because regression artifact increases. due to the regression artifact, not the treatment itself. So here's real life example, Head Start program. So the Head Start program was developed for low income children that would kind of begin the school-like system before kindergarten and preschool even. Um, and the idea there was that, well, if we can give them another year or two of, structured education, ideally we will see them perform better when they get to K through 12. Because we know that if you come from a low income family, you are less likely, it's not, again, a given, it's not destiny, just looking at the data, you are less likely to do well in school compared to your upper class counterparts. So Head Start program developed to fix that, ideally. So children above population mean selected for the Head Start treatment. So again, above population mean would be looking at poverty level stuff. Below population mean selected for control group. This introduced regression artifact. When retested, performance regressed to the mean of group. Treatment group performed worse on retest, control group performed better on retest. Results show no benefit or effectiveness of the Head Start program. And so what we kind of saw is that children in the Head Start program do tend to do better than or equal to their counterparts in like kindergarten, first grade, but eventually the effectiveness wears off. And so it's something that it looks really good at the start, but then the regression to the mean happens, and all of a sudden we don't see a positive effect of the Head Start program anymore. So way to fix it, random assignment. Again, if you're doing quasi experiments, you really can't do random assignment, but it is the way to try to get around regression to the mean. Okay, so want to switch over then to the other PowerPoint that's talking about interpreting results. And this one's going to look at convergence and reliability. So when we talk about reliability, this is the repeatability or consistency of expected results. So the idea of something being reliable is that a student is scoring consistently the same thing on that task or on that test as many times as you give it to them. If they are, we call that test to be reliable. If they are not, if they're scoring, all different scores, then we call that test unreliable. So test reliability, if I measure test performance and consistency, get the same results, my measure of test is reliable. If I measure test performance consistently and get different results, my measure would be then considered a poor measure. Ways to enhance reliability: large numbers of observations, greater reliability in study results of 1,000 versus 10 subjects. If you can get more participants in your study, if you're developing ideally a reliable test, having 1,000 in there is going to ultimately improve that reliability much more, or at least pan out if it's more reliable or not. And also repeatable, that you ultimately set up multiple studies to look at this to see, are people scoring the same across multiple studies. So here, when we look at experimental reliability, replication, conducting same study, different participants, and you find the same things. Replication, copy or reproduce. In psychology, it is unfortunately not done enough, that we run into replication issues quite frequently. And it's talked about, I know in your textbook, the reliability crisis, or excuse me, the replication crisis. And for good reason. Like, it absolutely is a big concern of psychology. I will just say, for what it's worth, my 2 cents is that while, yes, do we have some studies that are not being replicated like they should? Absolutely. I always look at it as we are studying human behavior, and human behavior changes, and ideally for the better. I mean, we don't always see that, but I would hope that a study that was done in the 1960s looking at human behavior on any aspect is going to yield different results in 2020. just due to the nature of ideally we've gotten better, right? That we understand things at deeper levels, and that's always going to be a big kind of mark on psychology. Is if our goal is to understand human behavior, replicating those studies, while incredibly important and it should at least be attempted, we need to understand that if something is not replicated, it might not actually be a flaw in any design or anything like that, but it's just people have changed over time. So example here, Einstellung, we try our habitual ways of solving a problem, even though more efficient procedures are available. Replicate this with water jar study, geometry problems, et cetera, et cetera. So really this is just looking at, do you constantly go through your same sets of, all right, I'm introduced with this problem and now I'm just going to do trial and error. I'm going to sit down and brainstorm. I'm going to go through this logically. What he found is that it doesn't really matter what's available to the participant. They're always going to go with their initial gut instinct to try to solve a problem. And he found that with multiple problems. So we have three types of replication: a direct one, repeating an experiment as closely as possible with as few method changes as possible; systematic replication, changing many factors irrelevant to phenomena to see if results don't replicate; and conceptual, replicate a phenomena in an entirely different way. So those three, again, each one is incredibly valuable. Each one has merit. It's just, what is it that you want to set out to do as a researcher? In psychology, we need to be careful about assuming replication. Most studies use white middle-class college students as subjects. Results won't necessarily be representative of other groups. Absolutely, that, I mean, because we have a bunch of college students that are scoring a certain way does not mean if we bring it out to, a different subset of the population, they're going to score the same. Differences can occur with age or culture. Should attempt to replicate samples of different cultures, ages, for assuming results are representative of other groups. So again, just important take-home messages about the replications. And then converging operations. Two or more operations that eliminate alternative concepts that might explain a finding. So if a finding is limited to one operational definition, the meaning of the concept is limited to that operation. Set concept, if only worked with water jars, concept is limited to water jars. Okay, so I want to kind of skip to here to go over converging operations in a little bit more detail. So converging operations can eliminate alternative explanations for findings. To find out if memory is affected by priming or motivation, test in the following situations. So each one of these could be its own study, or you might just have a very large study that has 4 different conditions. Priming is where you make something readily accessible. So it's done a lot in advertising. It's done a lot in kind of PR stunts and things that they want you to grab onto certain things. They prime you for it. So one of the things that are, very old study is that if you were primed by reading a spy book and then you were asked to come up with a definition of the word bug, you're likely to come up with something about bugging phone lines. If you were asked to read an article about insects and you were asked about the word bug, you were likely to define the word bug as some type of insect. You were primed differently, right, depending upon what you read first. And then motivation is obviously motivation to actually change something or to do something. So if you want to see if memory is affected by priming or motivation, you need to set up these different scenarios, see what type of things are going on, and do we have any converging operations. So situation 1 has priming with no motivation. Situation 3 has no priming and no motivation. If memory is better in situation 1 versus 3, we would then be able to say, okay, well, it looks like priming influences memory. Cool, but we still never actually looked at motivation. does that actually do anything? Because both conditions did not alter motivation at all. So here we can look at if memory is better in situation 2 versus 1, we would then say motivation influences memory. We now have convergence, right? That, all right, when we did priming and no motivation, we saw this effect. But when we did both priming and motivation, now all of a sudden we're getting increases. So we're getting this converging of priming and motivation working together. Especially if you've already done situation 3, and you now know like not doing priming is also detrimental, then situation 2 really becomes important to look at. Okay, so like I said, these were meant just to kind of fill the gaps from your textbook. If you have any questions about interpreting results, and again, this is not the look at the output stuff, but it's more the critical thinking. You have this finding, it says it's significant, but is it? Can you actually say that? Is there flaws, right? That type of stuff that I want you to be thinking about.